We now want to look at the stability of conjugated dienes as compared to isolated dienes. So we can do this by comparing the heat of hydrogenation. In other words, how much heat is given off when we hydrogenate using hydrogen with palladium on carbon as a catalyst. How much heat is given off when we do that hydrogenation. And for the isolated diene, you'll see here that this one gives off 255 kilojoules per mole of heat. In a similar fashion, if we do the heat of hydrogenation for this conjugated diene, you'll see that it only gives off 226 kilojoules per mole. That means because this gives off less heat and they have the same product, that means that the one that gives off less heat is more stable. And in this case, it is more stable by 29 kilojoules per mole. And it turns out that is quite a bit. We can look at it as an energy diagram. So both of these compounds give the same product when we do hydrogenation. But the less stable diene gives off more heat, which means it started from a higher energy. So what we want to do is we want to look at a couple of examples and determine which thing has the larger heat of hydrogenation. So we'll start with number 15 on the in-class assignment. Okay, so here it says which diene in each pair has the larger heat of hydrogenation. In other words, which one is less stable? Well, we know this one's conjugated and this one isn't, so this one is more stable. This one is less stable. And so this one has the larger heat of hydrogenation. So this one has the larger delta H of hydrogenation. All right. When we compare these two, well, this one is conjugated, this one is isolated, so the conjugated one is more stable. This one is less stable. And so that one has the larger delta H of hydrogenation. All right. And again, when we say it has a larger heat of hydrogenation, it has a larger negative value, so it gives off more heat. All right. We now want to look at addition reactions, electrophilic addition reactions. We talked about electrophilic addition in the previous semester back in chapter 8. Yes. Scratch that, it was chapter 10. But regardless, we talked about electrophilic addition. We talked about Markovnikov addition. So if you're not familiar with that, go back and look at chapter 10 and review that content. And I think you will find that enlightening. So when we're looking at electrophilic addition of HBr across an isolated diene, so here is an example of an isolated diene. Here we're adding just one equivalent. All right, I fixed a little typo there. It said on equivalent, one equivalent. So an electrophilic addition of one equivalent of HBr, we're going to get Markovnikov addition. That is, the hydrogen is going to go to the carbon that has the most hydrogen already. And you may remember the reason for that was the reason for Markovnikov addition was because it gives a more stable secondary carbocation. And so that is still true. We talked about that in the chapter on radicals. So what we want to do is we want to look at what happens when we have a conjugated diene. And what happens is that we get more than one product. So here with 1,3-butadiene and we add one equivalent, we are going to get two products. We're going to get what's called a 1,2 addition product. The 1,2 addition product is where the hydrogen and the bromine add across the carbon 1 and 2. And we'll also get what's called the 1,4 addition product, where when we add the hydrogen, it goes to carbon 1, but the bromine goes out to carbon 4. We get a mixture of these products. And since they are different, these are constitutional isomers of each other, we're not going to get a 50-50 mixture. Most likely we won't get a 50-50 mixture. And we'll actually talk about that here in just a few minutes. So here is the mechanism of 1,2 addition and 1,4 addition, why it is that we get both products. So, of course, when we do electrophilic addition, the first thing that's going to happen is that the pi bond is going to react with the hydrogen on the HBr, and so that hydrogen will go to the carbon that has the most hydrogens. The reason for that is that it will form a secondary carbocation as opposed to forming a primary carbocation. So we'll form the secondary carbocation. In addition to that, it also forms an allylic carbocation. And the allylic carbocation is even more stable than a regular secondary carbocation. So this allylic carbocation actually has two resonance structures. One resonance structure has the positive charge on carbon 2, and one of the resonance structures has the positive charge on carbon 4. Now, in reality, the hybrid structure has a partial positive on carbon 2 and a partial positive on carbon 4. And so it turns out the bromide can react with carbon 2, and in that case, it'll give what's called the 1,2 addition product. And if the bromide reacts with carbon 4, it will give the 1,4 addition product. So both of those products will form. Interestingly, when we have substituents on there, it can get even a little bit more complicated. And so we're going to look at what happens with various compounds. What kind of addition products are we going to get? So let's look at number 17. Go to our in-class assignment, number 17. So draw the products formed when each diene is treated with one equivalent of HCl. So if we add HCl, both of these are identical, so it doesn't matter which one it reacts with, but we will find that the hydrogen will go to the carbon so that we will form an allylic carbocation. So hydrogen is going to go here to that 2 position. And I'll go ahead and label this 1, 2, 3, 4, 5, 6, just so we can communicate about it. So the hydrogen is going to go to carbon 2, which again is going to be identical to carbon 5. Hydrogen will go to carbon 2. We will get a carbocation on carbon 3, but it will be in resonance stabilization with the carbocation where the positive charge is on carbon 5. So we will end up getting 2 products. And those 2 products could be 1, 2, 3, 4, 5, 6. So here hydrogen goes there. And if the hydrogen goes to carbon 2, then the bromide goes to carbon 3, this will be one of our products. So that will be one of our products. Now, if the hydrogen goes to carbon 2 and the bromide reacts with the partial positive charge on carbon 5, then we'll end up getting this. All right, and then just to be clear, we have 1, 2, 3, 4, 5, 6. And so here, this is our 1,2 addition product. All right, and this one is our 1,4 addition product. So the hydrogen ended up on carbon 2 and the bromine ended up on carbon 5, and that would be 1,4 addition. All right. And those are constitutional isomers of each other. And I couldn't tell you which one's more stable. They're about the same, so I wouldn't expect to get much more of one than the other. When we look at this one is a this one is an isolated diene. So when we treat it with one equivalent of HCl, the HCl is going to add across one of those. And it doesn't really matter which one it adds across. So I'm just going to arbitrarily pick this one. So it'll add across that. We'll get the electrophilic addition product. So we'll have the double bond there and a chlorine there. Technically, that would be a stereogenic center, but because we started off with an achiral starting material, we're either going to have an achiral product or a racemic mixture, so we would get a racemic mixture of this. But I did not indicate the stereochemistry, so we're just going to leave it like that. But if you're concerned, that's a stereogenic center, and we would have its enantiomer as well. All right, so now when we look at the next one, so HCl, we add that across this. This is a conjugated system. And just for numbering purposes, let's go ahead and we'll call this one 1, 2, 3, 4, 5, and 6. If we get 1,2 addition, we're going to get a chlorine that is here on carbon 2 and a hydrogen on carbon 1, and the double bond will be between carbons 3 and 4. And so our product would end up being that. All right. If you do the addition and you get 1,4 addition, then your double bond would be between carbon 2 and carbon 3, and the chlorine would end up on carbon 4. Well, it turns out that is the same product. So, so these are identical. So in that case, we only get one product. So it's the same product for both 1,2 addition and for 1,4 addition. All right, this one is a little bit more complicated because carbon 2 and 3 are different. And because carbon 2 and 3 are different, that means we're going to have a little bit more complicated mixture. So I'm going to call this 1, 2, 3, 4, 5, and 6. Now, in case you're curious, that is not how we would number it for naming purposes. And the reason for that is because the substituent would need to be on carbon 1. I'm not going to worry about that other than to say that's just how that is. But that said, if we were to do addition across this, and let's say that the hydrogen got added to carbon 1, then our possible places for the chlorine would be on carbons 2 and 4. So our products there so that's a methyl, and we would have the double bond still between carbons 3 and 4. Our 1,4 addition product would be this, where we would have the double bond in between carbons 2 and 3, and then we would have the chlorine on carbon 4. All right, and these are constitutional isomers of each other, so they would definitely be different products. But we could also get addition across the carbon 3, carbon 4 bond. If that happens, then the hydrogen would go to carbon 4, and the chlorine would go to either carbon 3 or carbon 1. So let's look at what that is going to mean. All right, so if the hydrogen goes to carbon 4 and our chlorine goes to carbon 3, then we have a methyl. We have a methyl there. All right, our other possibility here would be, let's see, our other possibility would be if the hydrogen went to carbon 4. All right, so there's our methyl. Hydrogen goes to carbon 4. We end up getting a double bond between carbons 2 and 3, and then the chlorine ends up on carbon 1. Well, if you look closely at these are the same product. So as far as our addition products, this one is 1,2 addition. This one was 1,4. This one was 1,2. This one was 1,4. But these two are the same. They are identical products. So we only get 3 products in this particular case. All right, so we now want to look at what we refer to as the kinetic pathway versus the thermodynamic pathway. So there's 2 different products that we can get when we're doing addition. All right, so when we do addition, again, there are 2 different products. One of the products, when we do this, is the 1,2 product. One is the 1,4 product. Interestingly, when we do this reaction at temperature slightly above room temperature, so at about 40 degrees Celsius, we get more of the 1,4 addition product. When we do it at very low temperatures, negative 80 degrees Celsius, so approximately, using dry ice temperatures, then we're going to get more of the 1,2 product than we get of the 1,4 product. When you get differences that are caused by differences in the amount of each product when you change the temperature, that usually indicates that one is a kinetic product and one is a thermodynamic product. And that's the case here. And so typically the one that is at low temperature is going to be referred to as the kinetic product. It has a lower activation energy. And the one that is at higher temperature, we're going to refer to as the kinetic product, or not the kinetic, but the thermodynamic product. So low temperature is usually kinetic, and high temperature is usually thermodynamic. And not usually, high temperature, you're going to get the thermodynamic product. The kinetic product, again, will happen at the low temperatures. So first of all, we want to understand, okay, why is this happening? And we can understand a little bit about why it happens by looking at a different reaction. What if we just take our 1,2 product, our 1,2 addition product that we had for the butadiene? And so this is our 1,2 addition product. If we take that up and heat it up to approximately 40 degrees Celsius, we're going to find that it will interconvert and get turned into the 1,4 product. And this is going to be an equilibrium condition. So if you heat it up to a higher temperature, you get the thermodynamic product. You get the equilibrium product. So we'll find that the 1,2 product forms faster and is favored at low temperatures, and the 1,4 product is more thermodynamically stable, therefore it's the thermodynamic product, and will predominate at equilibrium. And so this helps us to understand what's going on. So let's look at an energy diagram. So we're looking at the energy diagram, but just for our second step. Our first step is the addition of H plus to the carbon-carbon double bond, to our conjugated system. And our second step is the addition of our halide. In this case, it was chloride. So the addition of our halide to that carbocation intermediate, the allylic carbocation. And we'll find that these have different energy profiles. So if we look at the kinetic pathway, which is the blue one here. So we look at the kinetic pathway. At low temperatures, we're not going to have as many molecules getting up to the higher activation energy, so we'll have a slower flow of molecules that are going over this pathway, and so more molecules will follow this lower energy pathway, even though it gives us a product that is less thermodynamically stable. If we do it at higher temperatures, we're going to get more molecules capable of going over this higher pathway, and we will get the more thermodynamically stable product. Interestingly, if we were to take this and heat it up, what would happen, the thing that we did on the previous page, if you heat up the kinetic product just by itself, it will get converted back into the carbocation, and at the higher temperature, when the bromide adds back to it, when you get that nucleophilic attack on the carbocation, you will end up getting our thermodynamic product. So you can kind of think of this as when you heat this up, it goes back up the hill and then comes back down, going to our lower energy product. So as I was mentioning, this is just the second step of our addition. The first step is adding the H plus to the conjugated diene, and that is going to be our rate determining step, which we will look at here in a moment. I do want to say, why is that 1,4 product more stable? Hopefully by this point you can recognize why it's more stable. It's a more substituted alkene. More substituted alkenes tend to be a little bit more stable than like monosubstituted alkenes. Well, our 1,2 addition product is monosubstituted. Our 1,4 addition product is disubstituted. Since it's disubstituted, it's more thermodynamically stable, and therefore it is the thermodynamic product. The way that we get the 1,2 addition product is something that we call the proximity effect. So the 1,2 product forms faster because the bromide just happens to be closer to carbon 2 after you've added the hydrogen to carbon 1. So again, here is our starting material, the 1,3-butadiene. The hydrogen adds to that carbon-carbon double bond, or the pi bond. The hydrogen is going to go out to carbon 1, forming our allylic carbocation, but the bromide is right there, if it hasn't really moved. And so that bromide, because it's so close to carbon 2 at low temperatures, is more likely to react with carbon 2, even though that's going to give us a higher energy product. So that bromide would have to migrate a little bit to get over to carbon 4. That said, even at low temperatures, we're going to get a significant amount of these bromide anions reacting with carbon 4, which is why we get about 20% of the thermodynamic product, even at those really low temperatures. But this is how we can get more of our kinetic product. All right, and now I want to put it all together so you can see the energy diagram for the whole process. So as I mentioned, the first step is the rate determining step. It has the largest activation energy of our 2 steps, regardless of what our second step is. This first step is rate determining. And so once the molecule has formed the carbocation, then it's a relatively small difference between these, which is why we still get a significant amount of the 1,4 product, even at low temperatures. But that higher activation barrier does slow down that pathway at low temperatures, meaning that we get more of our kinetic product than we do of our thermodynamic product. So at low temperatures, it goes over the lower pathway. At high temperatures, it goes to equilibrium. All right, so we're going to look at 19. 19 is actually the same problem, but it's only one set of the products. So it's the same one that we had here. We end up getting these 2 products are the ones that are indicated right here. It does not show this product. It is probable that we wouldn't get very much of this product because this pathway gives us a tertiary carbocation, whereas this pathway only gives us secondary carbocations. Now, admittedly, it's a tertiary allylic carbocation, and this one's a secondary allylic, but we're more likely to follow this pathway, which is why we only show these two products on this problem. But keep in mind, this can form, and probably does to some extent, but I don't know how much. That said, we want to label each product for the following reaction as a 1,2 product or a 1,4 product. Well, we have already done that part, right? When it adds across this bond, that's the 1,2 product. So 1,2, and this is the 1,4 product. All right, since this is the 1,2 product, that means it is the kinetic product. And because this one is 1,4 addition, this is the thermodynamic. All right. So there is that. All right, and the reason this is the thermodynamic product is, if you look here, it's a more substituted alkene. This is a tri-substituted alkene, whereas this one is only a di-substituted alkene. So that's why that one is the thermodynamic product. Okay, so we're going to look at a really cool reaction that is called the Diels-Alder reaction. And I really love the Diels-Alder reaction because it seems, I don't know, the first time you see it, it seems almost kind of magical. It seems like something that shouldn't be able to happen, but it definitely does. So the Diels-Alder is an addition reaction between a 1,3-diene and an alkene. Because the alkene reacts with a diene, we call it a dienophile. So here is our 1,3-diene, and here is our dienophile. So when this reaction occurs, we can indicate the movement of electrons by using the curved arrow notation that we're quite familiar with. I typically will draw it in the same counterclockwise manner, but it turns out it doesn't really matter. You could do clockwise or counterclockwise. You're going to get the same thing. The important thing is to draw the arrows from the right place to the right place. We're going to draw this arrow from the double bond that is in the dienophile to one of the carbons in our 1,3-diene. And it has to either be carbon 1 or carbon 4. If you're going this way, it's going to be this top carbon. Then we're going to take that pi bond between carbon 1 and 2 and move it to carbon 3, 4, or 2, 3, and put a double bond there. Then we're going to take the pi bond in between carbons 3 and 4 and draw it so it goes to the carbon. So again, from this pi bond to this carbon, from this bond to this bond, and from this bond to this carbon. And the reason that we're doing it is because we're making 2 new sigma bonds. So we need to go to the carbon when we're making those sigma bonds. When we're making a new pi bond, we draw to the sigma bond that's already there to create that pi bond. In the process of doing this, this is kind of important. In the process of doing this, we're going to break 3 pi bonds, and we'll make 1 new pi bond and 2 new sigma bonds. Well, sigma bonds, generally speaking, are stronger than pi bonds. And that's definitely the case as what is happening here. So the sigma bonds are stronger than the pi bonds, and because that is the case, we are going to get, it's going to release heat when this occurs. So we will release heat when we do this reaction. Interestingly, in addition to releasing heat, we also need to add heat to make it happen. We'll talk about why that is a little bit later, but the simple answer for that is that this requires us to add heat to overcome the high activation barrier for this reaction to occur. Now, it's a high activation barrier for this particular reaction, and we will see that there are some cases where the activation barrier is not as high and you don't really have to heat it. But we generally do heat it to make it go faster. All right, so that's the Diels-Alder reaction. Now, I'm going to show you a molecular model here. All right, and with the molecular model, switch over here. So here, this is the Darling molecular model things that I have shown on previous videos before. So here we've got a diene. Notice that this diene is in the S-cis configuration. If it's an S-trans, it won't work. We'll talk about that later, but it won't work. And here we've got ethylene, and we'll find that what happens is that this will come either above or below, but they don't come on the same plane. So we won't find that they're on the same plane. It's either above or below. So when it comes in, the pi bond that is here will interact with the pi bonds that are in the diene, and we will get new bonds in between these carbons. So I'm also going to show you another molecular model. These are the models that I made, that I designed and 3D printed. Here we go. And so with these, we can kind of see the p or the pi bonds a little bit better. And so here we've got the pi bond that is above and below on this ethylene, the dienophile, and then here is our diene. And again, it comes in above, and we start to get an overlap between the pi bond here and there, and the pi bond here and here. And when we do that, the electrons will move around. So this pi bond will make a sigma bond in between these two carbons. This one will come over to make a pi bond between these two carbons. And this pi bond will go over to make a new sigma bond with this carbon. So I think it's helpful to kind of visualize what's going on. Again, one of the important features of this is that it does have to be in the S-cis conformation. If it is in the S-trans conformation, we don't get the Diels-Alder reaction. It only happens when it is S-cis. All right, so here is a typical example of a Diels-Alder reaction with a good diene and a good dienophile. You'll notice that these dienophiles have substituents on them, and typically we'll find that those substituents are going to be things like carbonyls. You can do nitrile. There's a couple of other examples, but it usually is something that has a pi bond and something that is electron withdrawing. Because that oxygen is so electronegative, it pulls electron density away from this carbon-carbon pi bond in the dienophile. I'll explain why that's useful a little bit later, but this is going to be our Diels-Alder product when we do this reaction. Similar fashion here, we'll get the new product here, we'll form the new bonds. So we want to look at an example where people have used the Diels-Alder in a synthesis. And so this is a very complicated compound. This is it is a toxin. When you eat it, it may be the last thing you do. It's a quite deadly toxin. It is found in Japanese pufferfish. You may have heard about pufferfish. If it is prepared by somebody who doesn't know what they're doing, you may end up getting this toxin, and it could be, like I mentioned, it can be deadly. Well, one of the steps in the synthesis of this toxin, and you may think, well, why would they want to produce something so deadly? It turns out if something is toxic, it also may be useful for other things. And so this may be a starting point for other therapeutic compounds that maybe could fight cancer. I don't know exactly what it's used for, but that is an example of how you could use it. So they do this Diels-Alder, and when they do the Diels-Alder, and notice the stereochemistry there. We're going to talk about that stereochemistry here in a bit. But you notice that this is cis fused, so we'll talk about that. You make this product, and then using many steps, which is a lot of time of some poor grad student or postdoc's life, they made this particular product, which they can use to do studies on. So we want to look at a couple of features of the Diels-Alder reaction. So what makes it what makes it work? Well, first of all, one of the important features is that it's initiated by heat. You have to heat up most of these to make them work. There are a couple that will work at room temperature, but those are the exception rather than the rule. Most of them you have to heat up to high temperature. Even though they're exothermic, if you don't heat them, it doesn't get over the activation energy. Another feature is that they form six-membered rings. Well, forming six-membered rings is a very valuable synthetic process. So if you can find a way to form six-membered rings, that is going to help you. That's going to help you be able to do synthesis. Our third thing is we break 3 pi bonds, and then we make 2 new sigma bonds and 1 new pi bond. And so you want to be able to recognize what that bond is going to look like, and what that ring is going to look like. And then finally, and this is important, these are concerted reactions. And we've talked about concerted reactions before. For example, the SN2 is a concerted reaction. We make and break the bonds at the same time. Well, in this, it's also concerted. All 3 pi bonds are broken at the same time, and the 2 new sigma bonds and the new pi bond are formed all at the same time. And so because it's concerted, that's going to have some effects on stereochemistry, and we'll talk about that shortly. So how to draw a Diels-Alder product. The first thing is that you want to take your diene and rotate it around so that it is in the S-cis conformation. We're going to talk about this a little bit more in the next section, but for now we'll just say it needs to be in that S-cis conformation before before we can do the reaction. So we'll need to take it and rotate it around. And for simple compounds, that's super easy to do. And then you'll want to line up the dienophile so that it is adjacent to our diene, and then that makes it easy to do the curved arrow notation to help us show where the bonds are broken and made. Once you do that, you do curved arrow notation and you draw your new Diels-Alder product. Here it just shows which atoms, so the red atoms are the red atoms here, and then the blue atoms, which are at the 1 and 4 position of our diene, are the blue atoms here. So once you do that, that's also going to make it easier to do retrosynthesis with the Diels-Alder, which we're going to do here in a coming section. Let's look at number 20, and this will give us some practice, drawing Diels-Alder products. All right, so here we've already got this one in the S-cis conformation, so I'm going to go ahead and just redraw it. So that's already in the S-cis conformation. And then we've got our dienophile, and I'm going to rearrange it a little bit. So we've got the double bond ready to go. All right, so that's typically how you'll see it drawn. And then we're going to do the arrows. Now, if you're just trying to draw the product, this one didn't specify that we needed the arrows, but I'm going to do the arrows because I do want you to know how to do the curved arrows. Anytime you do a mechanism, you need to show the curved arrows. So we're going to go from this pi bond, and we're going to make a new bond with this carbon. So I'm going to go from this pi bond to that carbon. I didn't curve that arrow very much, but I forgive myself. Then we're going to take this pi bond and move it to between carbons 2 and 3 to make that new pi bond. And then we'll take the other pi bond, and it's going to react with this carbon. And so we'll make a new sigma bond. So we'll have a new sigma bond here and here, and then we'll have a new pi bond here. So you can draw your six-membered ring. All right, our new pi bond is right there. We already had methyl groups there and there. And then here at this carbon, we're going to have our carbonyl and OH. Now, one thing I'm going to point out real quick, we did create a new stereogenic center. And I keep saying this over and over again because I want to make sure that you understand. Anytime you have achiral starting materials, like we do here, you're either going to have an achiral product, or you'll have a racemic mixture of products. And in this case, we're going to have a racemic mixture. So I'm just going to put plus enantiomer just for completeness. All right, so that's going to be our product plus our enantiomer in case we're curious. All right, for this next one, we need to rotate this one around so it gives the S-cis conformation. All right, so there's our butadiene. It's an S-cis conformation. We'll go ahead and put our dienophile all right, I'm going to draw that double bond a little bit longer there. And now we're going to do our curved arrows. So again, I always start with the dienophile, although you can start with any of the pi bonds that you want, but I always start with the dienophile. And we're going to draw from that bond to this carbon, from this pi bond to this bond to make a new pi bond there, and then from this pi bond to that carbon. And so that will be our new ring. All right, so there is our new ring. We don't have any substituents on here, so we won't have anything there. But over here, we will have a methyl and a carbonyl, that is this ester. All right, since that technically is a stereogenic center, I am going to put plus enantiomer for completeness sake. All right, we've got one more in this section here. Ooh, they switched it up. They put the dienophile first, and it doesn't matter what order you put them in. I like to draw it the same way, but as far as the molecules they're all thrown in a flask. They don't really have an order. So I'm going to put this in our S-cis conformation. And this is actually the same diene as the one that was here. It's just drawn differently. All right, so this and this. All right, and then our dienophile, the carbon-carbon double bond, our carbonyl, and that. So that's our methyl vinyl ketone. All right, so now we'll do the arrows. We'll go from this pi bond to this carbon, from this pi bond to make a new pi bond there, and then from this pi bond to this carbon. All right, our product is going to have a six-membered ring. That is one of the key important features of the Diels-Alder reaction. And on this carbon, we're going to have our substituent, which is this. And again, we have a stereogenic center there, so I'm going to put plus enantiomer. Even though I did not draw individual enantiomers here, I go ahead and put plus enantiomer just so everybody's clear. You do get a racemic mixture. All right, well, that is a good place to stop for the second video. In the third video, we're going to talk more about the Diels-Alder and wrap up chapter 14.